A cosmic whirlpool of stars spins in perfect harmony for billions of years. How does such chaotic matter arrange itself into such breathtaking order? We are going to uncover the hidden mechanisms that shape spiral galaxies. You will learn the fundamental cosmic forces that build these celestial masterpieces, what invisible architecture holds these star cities together, and why does their beautiful structure refuse to fade away over time? What does the enduring order of a galaxy tell you about the universe itself? That initial structure of a bustling cosmic city is not a static arrangement. It is a dynamic and fluid system constantly in motion. Each star, each cloud of gas, follows its own orbital path around the galactic center, much like cars on a vast circular freeway. But here is where a profound mystery begins. If every star is simply orbiting independently, why do we see such coherent, long-lasting spiral arms? These arms are not solid structures. They are not like the rigid spokes of a wheel. Think of them instead as a cosmic traffic jam, a pattern of density that moves through the galaxy. This pattern is a wave, a ripple in the very fabric of the galactic disk. And just as a wave can travel across the ocean while the water itself mostly stays in place, this spiral density wave travels through the field of stars. As stars and gas clouds enter this wave, they slow down, bunching together and igniting the brilliant blue light of new stars. They then pass through the other side, continuing their journey. This is the first hidden mechanism, the great organizer that imprints order onto the chaos. It explains why the spiral arms seem so bright and defined, and why they persist for eons without winding up into a tight knot. The galaxy is not a solid object turning. It is a symphony of motion with a silent conductor shaping the music. But what is it that orchestrates this grand symphony of motion? The spiral density wave is a magnificent conductor, yes, but it needs a stage on which to perform. That stage is built by a far more elusive and powerful entity, an invisible architect whose presence we can only infer from its overwhelming influence. This cosmic phantom is dark matter. It is a substance that does not emit, absorb, or reflect any light, making it completely undetectable to our telescopes. Yet, we know it is there because of the immense gravitational pull it exerts on everything we can see. Think of it as the unseen foundation of a vast, invisible city, a metropolis whose outline we can only map by watching the paths of the stars moving within its gravitational streets. This dark matter forms an enormous, diffuse halo that envelops the entire visible galaxy, a sphere of influence that extends far beyond the bright disk of stars. It is this halo's profound gravity that provides the crucial scaffolding, dictating the speed at which stars orbit and ensuring the overall stability of the galactic disk. Without this unseen framework, the delicate spiral arms we admire would simply not hold together. The entire galaxy would risk flying apart, its stars scattered into the void. So while we watch the beautiful dance of the stars and gas, we are really seeing a performance directed by an invisible hand. The luminous galaxy is just the visible expression of a much larger, hidden structure. This persistent wave is a gravitational phenomenon, a kind of cosmic rhythm that orchestrates the chaos. To grasp its nature, think of that circular highway again, but this time envision a traffic jam that does not move with the cars. It simply exists as a stationary pattern of congestion. The cars enter the jam, slow down, and bunch together before eventually speeding up and leaving it behind. The jam itself remains a fixed structure on the road. This is the brilliant insight of the density wave theory proposed by astronomers like C. Lin and Frank Shu. The majestic spiral arms we see are not solid arms of stars that turn like a pinwheel. They are rotating patterns of compressed density, moving through the galactic disk at their own, slower pace. As countless stars and massive clouds of gas orbit the center, they journey into this gravitational ripple. The wave acts like a cosmic press, squeezing the interstellar gas. This compression triggers a spectacular chain of events, igniting the birth of brilliant, short-lived blue stars that blaze with intense light, outlining the arm in a fiery signature. These stars are so luminous they define the arm's shape, but they burn out long before they can travel far. They live and die within the pattern, while older, dimmer stars simply pass through it unharmed. This elegant dance between the independent motion of the stars and the persistent pattern of the wave is what carves the galaxy's grand design. It solves the winding problem, explaining why the arms do not simply twist up and vanish over billions of years. The pattern endures even as every participant within it is constantly moving. Yet this revelation only deepens the mystery. What fuels this persistent wave, keeping this cosmic rhythm from ever fading away? Yet for this grand cosmic wave to paint its light across the void, it requires more than just a pattern. It needs pigment, a raw and vibrant material to bring its design to life. That essential substance is the interstellar medium, a vast and drifting sea of gas and dust that fills the spaces between the stars. Picture immense, cold clouds of hydrogen and helium, laced with fine grains of silicate and carbon, drifting silently through the galactic disk. This is the primordial stuff of creation, the very fuel from which stars are born. When a star-forming cloud enters the gravitational squeeze of a spiral density wave, something spectacular happens. The gas is compressed, its atoms forced closer together. This increase in density is the trigger for a monumental collapse. Under its own growing weight, a pocket of gas begins to contract, spinning and flattening into a disk. At its core, pressure and temperature skyrocket until they cross a fundamental threshold, igniting the furnace of nuclear fusion. A new star blazes into existence. This is why the spiral arms appear so brilliantly defined. They are not just traffic jams for stars, they are cosmic nurseries, lined with these brilliant, short-lived blue giants that blaze with an intensity that outlines the arm in fire. This ongoing cycle is absolutely vital. The spiral pattern provides the gravitational blueprint, but it is the collapse of this gas and dust that provides the light, making the invisible architecture of the wave visible to us across the depths of space. The galaxy is constantly consuming its own fuel, transforming these mundane clouds of cold gas into the most radiant beacons in the universe. But what determines where and when these engines of creation ignite? What are the final, local triggers that turn a quiet cloud into a stellar inferno? The brilliant blue giants born in the spiral arms are more than just temporary residents. They are cosmic engines whose brief, violent lives actively shape the very architecture that created them. Think of it as a chain reaction of celestial fireworks, where one colossal explosion triggers the next in a breathtaking, self-perpetuating display. These massive stars live fast and die young, burning through their nuclear fuel in just a few million years, a mere blink in cosmic time. Their spectacular end comes in the form of a supernova, a titanic blast that rips through the surrounding space. The shockwave from this stellar detonation slams into nearby clouds of gas and dust, compressing them with unimaginable force. This violent squeeze is the ultimate trigger, pushing these clouds over the edge of gravitational collapse and igniting a new generation of stars. This is a powerful feedback loop, a cycle of creation born from destruction. The spiral density wave creates the initial conditions for star birth, and the resulting supernova then reinforce the wave, maintaining the sharp contrast between the vibrant, dense arms and the quiet, dark spaces of the galactic disk. The energy and momentum released by these stellar engines continually sculpt and redefine the galactic landscape, carving out vast bubbles and filaments. This reveals a profound truth about the cosmos, that order is not a passive state. It is an active, dynamic process where creation and destruction are two sides of the same coin, locked in an eternal dance. How can such a violent, explosive system possibly remain stable for billions of years without either burning out all its fuel or tearing its own beautiful structure completely apart? This relentless pull of differential rotation is a force of cosmic dissolution. Picture the galaxy not as a solid disk, but as a fluid, with every star and cloud of gas following its own independent orbit around the central hub. Just like planets in a solar system, objects closer to the center complete their orbits much faster than those far out in the galactic suburbs. This variation in orbital speed creates an effect known as galactic shear. Think of it as spinning a ball of pizza dough by its center. The outer edges stretch and thin out dramatically, wrapping around themselves, while the inner parts rotate with less distortion. Now apply that same principle to a nascent spiral arm. If that structure were simply a chain of stars moving together, the inner part of the arm would rapidly overtake the outer part. Over a few 100 million years, what began as a graceful spiral would be wound up into a hopelessly tight, indistinguishable coil, like a string being wrapped around a spool. The beautiful architecture would be erased by the simple mechanics of orbital motion. And yet, when we look at galaxies across the universe, we see their spiral arms standing strong, defiantly open and defined for billions of years. Their very persistence is a profound clue. It tells us that the spiral pattern we observe is not a physical structure being wound up, but something else entirely. A pattern that is constantly being regenerated, fighting a continuous battle against the galaxy's innate tendency to tear itself apart. This tension between the destructive force of shear and the creative force of pattern formation lies at the very heart of the mystery. It forces us to look beyond the local chaos of stellar births and supernova toward a larger, more fundamental influence that orchestrates the entire galactic dance from behind the scenes. Sometimes the most beautiful order does not emerge from solitude, but from a violent encounter. A galaxy can live for billions of years in relative peace, its spiral patterns gently self-sustaining. But when another galaxy ventures too close, that delicate balance is shattered, and a new kind of order is forged in the chaos of a gravitational duel. These are not head-on collisions in the traditional sense, where stars physically smash into one another. The distances between stars are far too vast for that. Instead, it is a gravitational dance, a close pass where the invisible force of gravity itself becomes a sculptor's tool. As the two galaxies swing by each other, they exert tremendous tidal forces, pulling and stretching one another. These forces can reach deep into a galaxy's heart, plucking stars from their orderly orbits and dragging vast rivers of gas out into long, streaming arcs. It is this very disruption that can instigate or dramatically enhance a spiral pattern. The gravitational disturbance acts as a trigger, seeding the initial asymmetries and funneling immense amounts of gas toward the galactic center. This sudden influx of fuel can ignite a firestorm of new star formation, a starburst that lights up the spiral arms with a ferocious intensity. The encounter essentially gives the galaxy's density wave a powerful external kick, setting its rhythm for eons to come. Our own Milky Way, for all its current calm, bears the scars of such ancient interactions. The delicate warp in its outer disk and the vast streams of stars orbiting its halo are silent testimony to past mergers with smaller dwarf galaxies. These events were not destructive ends but formative chapters. They reshaped our galactic home, funneling gas and potentially even providing the initial nudge that helped establish its magnificent spiral arms. This reveals a profound truth about cosmic architecture. A galaxy's current appearance is not just a product of its internal physics. It is a living record of its history, a story written in the gravitational interactions with its neighbors. Isolation is not the cosmic norm. Community and occasional conflict are the true sculptors of the grand design we see etched across the night sky. That anchor at the galaxy's heart, the central bulge, is far more than a simple destination. It is the gravitational keystone of the entire system, a dense, spherical swarm of ancient stars that acts as the galaxy's anchor. Picture a vast ship, its heavy hull stabilizing it against the relentless ocean waves. The central bulge plays a similar role for the galaxy, its immense mass creating a deep and stable gravitational well that influences every star and cloud of gas within the disk. This central concentration of mass dictates the overall rotation curve, the speed at which stars orbit at different distances from the core. It is this gravitational blueprint set by the bulge that either suppresses chaotic instabilities or allows for the graceful, persistent patterns of the spiral arms to emerge. In many spirals, this central region evolves into something even more dynamic, a bar. This is a straight, elongated structure of stars that cuts directly through the galactic center, like the central bar of a giant celestial T. This bar is not a static ornament. It rotates, and as it turns, it acts as a powerful gravitational engine. It funnels immense rivers of interstellar gas inward from the disk toward the core, compressing the gas and triggering furious waves of star formation. This influx of material and energy can directly drive and sustain the spiral arms that spring from the bar's ends, so the core is not a silent, retired king. It is an active, bustling metropolis whose gravitational influence reaches out to shape the entire kingdom, orchestrating the flow of gas and the very rhythm of the spiral density wave. This leads us to a final, captivating question. With all these mechanisms at work, from the invisible hand of dark matter to the stellar feedback and the central anchor, what determines the ultimate form a galaxy takes? Why do some spirals present such perfect, symmetrical pinwheels, while others show broken, flocculent arms or even take on the dramatic shape of a barred spiral? That great cosmic mixer at the galaxy's heart, the central bar, is a powerhouse of motion. It transforms the gentle flow of the galactic disk into a directed, energetic river. Imagine a vast, rotating stirrer made of billions of stars, its gravitational reach immense. As stars and gas clouds orbit the galactic center, they do not move in simple circles. Their paths are constantly tweaked and tuned by the bar's persistent gravitational pull. This interaction forces them into resonant orbits, specific pathways where the rhythm of their motion locks into harmony with the bar's own rotation. It is a gravitational dance where energy and momentum are systematically traded. The bar acts as a cosmic pump, effectively siphoning gas from the outer disk and channeling it on a dramatic journey inward toward the galactic nucleus. This inward flow is a critical delivery of star-forming fuel, but the bar's influence does not stop there. This same pumping action can also drive material outward, creating intense pressure and density at the bar's very tips. It is at these pivotal points that the grand spiral arms often begin, springing forth as if directly launched by the bar's relentless motion. Here, the funneled gas is compressed to its breaking point, igniting brilliant hubs of star formation that trace and reinforce the spiral pattern. This makes the barred spiral a marvel of self-sustaining cosmic engineering. The central structure is not a passive anchor, it is an active driver, a dynamic engine that continuously works to maintain the galaxy's beautiful, orderly design. Gravity may be the dominant architect, but it does not work alone. Another invisible force weaves its way through the vast expanses between the stars, a subtle but persistent presence known as the galactic magnetic field. Think of it as a cosmic web of faint threads, a pervasive network of energy that permeates the entire interstellar medium. While its pull is millions of times weaker than gravity's grasp, its influence is nonetheless profound. It works on the smallest scales, meticulously aligning microscopic dust grains so they spin in a preferred direction, and on the grandest scales, guiding the flow of ionized gas as it courses through the spiral arms. In the turbulent, compressed regions of a density wave, this magnetic architecture acts as a delicate skeleton. It provides a form of pressure, a gentle resistance that can help support a gas cloud against its own weight, subtly influencing how and when it collapses to form new stars. This force can also channel the chaotic motions of supernova-shocked gas, helping to sculpt the long, filamentary structures we observe and potentially reinforcing the sharp boundaries of the spiral arms themselves. It is a reminder that the beautiful order of a galaxy is not the product of a single, overwhelming force, but a delicate interplay of multiple, interconnected systems. The grand design emerges from the constant negotiation between the crushing power of gravity, the explosive feedback of stars, and the silent, guiding hand of magnetism. Long before the first star ignited, the stage was set by a single, unchangeable property, a cosmic heirloom passed down from the birth of the universe itself. This is angular momentum, the primordial spin that every galaxy carries. You can think of it as a cosmic budget of rotation, a fixed amount of spin that a system possesses. The key is that this budget is conserved. It cannot be created or destroyed, only transferred and transformed. The slight, random tumble of a vast, collapsing cloud of dark matter and gas in the early universe contained a tiny, almost imperceptible amount of this spin. As gravity pulled this cloud inward over millions of years, this conservation law took over. Just as a figure skater pulls their arms in to spin faster, the collapsing cloud began to rotate more and more rapidly. This increasing spin forced the cloud to flatten, fighting against gravity's pull from all directions. The result was a vast, thin disk, a cosmic whirlpool of gas and dust. This is why spiral galaxies are flat and why they rotate at all. That initial, faint rotation from the dawn of time is the reason you see a majestic pinwheel instead of a formless, spinning sphere of stars. It is the fundamental canvas upon which the dark matter halo, the density waves, and the stellar fireworks all paint their masterpiece. Without this inherited spin, the beautiful, dynamic order of a spiral galaxy would have no foundation upon which to form. So when you look at a galaxy gracefully turning in the void, you are witnessing the echo of its very first moment, a memory of a collapse that never forgot how to spin. Lurking at the very heart of this magnificent whirlpool, at the center of the ancient bulge, resides a gravitational singularity of almost unimaginable power. A supermassive black hole anchors our galaxy and nearly every other massive spiral. It is easy to cast this entity as a purely destructive cosmic monster, a voracious pit that consumes all it touches. But the truth is far more nuanced, and its influence on the galactic design is profound. When this silent monarch awakens to feed, it does not consume quietly. Vast reservoirs of gas and dust funneled inward by the galactic bar swirl into an incredibly hot, bright disk around the black hole. This process can trigger an eruption of energy, transforming the core into a quasar or an active galactic nucleus. The outpouring of radiation and powerful particle jets can be so intense that it heats the surrounding interstellar gas, or even blows it completely out of the galactic center. This phenomenal act of feedback effectively starves the inner regions of the fuel needed to form new stars. It is a self-regulating mechanism, a cosmic thermostat that prevents the central bulge from growing too large too fast. By limiting star formation in the core, this active phase helps preserve the delicate balance between the bulge and the disk, a balance crucial for maintaining the galaxy's overall spiral structure. In its more common quiescent state, the black hole is a sleeping giant. Its overwhelming gravity simply adds to the central mass concentration, helping to anchor the entire galactic rotation and stabilize the gravitational well that guides the density wave. So this ultimate cosmic paradox, an object defined by its ability to trap light, is not just a passive occupant. It is a key player in the galactic ecosystem, its occasional violent outbursts serving to regulate the very growth of its own kingdom, ensuring the grand spiral design endures for eons. But how can we possibly test a cosmic dance that unfolds over billions of years? The answer lies not only in our telescopes but in our computers. We have built digital laboratories where entire universes are born and evolve within the memory of a supercomputer. These are not simple animations, they are sophisticated cosmological simulations that model the very fabric of reality. They begin with millions, even billions of particles, each representing a parcel of dark matter, a cloud of gas, or a cluster of stars. The laws of physics, from gravity to hydrodynamics, are programmed in, and then the simulation is set in motion, fast-forwarding through cosmic time. Inside this virtual cosmos, astronomers can watch as a formless cloud of dark matter begins to collapse, as a galactic disk spins into existence, and as the first delicate spiral arms slowly emerge from the chaos. They can tweak the initial conditions, subtly altering the amount of dark matter or the strength of supernova feedback, and then observe the consequences. Does a bar form? Do the spiral arms become tight and graceful or broken and flocculent? These simulations have been crucial in validating the density wave theory, showing how a spiral pattern can persist for eons without winding up. They allow us to see the competitive tug of war between the stabilizing pull of the dark matter halo and the disruptive energy of stellar explosions. We can witness first and how a galactic merger can trigger a new spiral pattern, or how a central black hole's outburst can quench star formation. These digital universes provide a dynamic, testable narrative, a grand experiment that shows how all the hidden mechanisms, from the invisible hand of dark matter to the violent feedback of stars, conspire together to sculpt the majestic spiral galaxies we see from our tiny vantage point. They are our closest tool to a time machine, allowing us to watch the universe write its own history, one line of code at a time. The invisible architecture of a galaxy reveals itself across the entire spectrum of light. Our most powerful telescopes act as cosmic translators, decoding the specific languages of infrared, radio, and ultraviolet radiation to expose the hidden mechanisms at work. The iconic visible light images from the Hubble Space Telescope show us the grand design, the breathtaking swirl of stars and dark dust lanes. But to see the underlying structure, we must look deeper. The James Webb Space Telescope, with its infrared eyes, pierces straight through those obscuring dust clouds, revealing the ghostly skeleton of older stars that form the true backbone of the spiral arms. Meanwhile, vast arrays of radio telescopes on Earth listen to the faint whispers of cold atomic hydrogen, tracing the distribution of the raw, star-forming fuel as it flows through the density waves. Ultraviolet observations, in contrast, act as a spotlight for violence and youth, pinpointing the brilliant, short-lived blue giants that mark the most active stellar nurseries. By weaving these different views together, astronomers create a multi-dimensional map of a galaxy's anatomy. They can trace the subtle gravitational tug of dark matter by precisely measuring the rotation speed of stars and gas at different distances from the center, confirming that the outer regions orbit far too quickly unless an immense, unseen mass is holding them in. We can literally watch the compression of gas clouds within a spiral arm, followed by the brilliant ignition of new star clusters, directly observing the feedback cycle that shapes the galactic landscape. This is not abstract theory, it is a story written in light and energy, a narrative we can now read with stunning clarity across the vast expanses of interstellar space. This enduring puzzle, the winding problem, has challenged astronomers for generations. If the spiral arms were simply chains of stars moving in lockstep, the galaxy's own rotation would destroy them. The inner stars orbit the galactic center much faster than the outer stars. Over a few 100 million years, this differential rotation would stretch any physical structure into an impossibly tight coil, wrapping it beyond recognition. A spiral galaxy would, by all rights, should twist itself into a featureless, blurry disk in a cosmic blink of an eye. And yet, when we look out, we see countless galaxies with their arms wide open, their grand designs preserved for billions of years. Their very existence is a defiance of simple orbital mechanics. This paradox is the key that unlocked a deeper truth. The spiral arms are not things. They are not solid structures you could touch. They are patterns, like a standing wave in a river or a traffic jam on a highway. The cars enter the jam, they slow down and bunch up, creating a visible cluster of congestion, but then they eventually leave while the jam itself remains in place. The pattern persists even though every single participant within it is constantly moving. This is the brilliant insight of the density wave theory. The majestic spiral is a gravitational ripple, a pattern of compressed density that moves through the galactic disk at its own, more stately pace. The stars and gas are the participants. They flow into this wave, get squeezed to trigger star formation, and then flow out the other side while the wave itself endures. This is how the galaxy solves the winding problem. The pattern is not being wound up because it is not tied to the orbital motion of the stars. It is a separate, persistent rhythm imprinted upon the disk, a rhythm that somehow manages to resist the galaxy's innate tendency to shear itself apart. This solution, however, only deepens the mystery. What is the source of this rhythm? What cosmic metronome keeps this grand pattern beating for eons, ensuring the spiral arms never fade away? These resonant orbits are the gravitational architecture that gives the spiral pattern its longevity. Picture a child on a swing. If you give a small push at just the right moment in the swing's arc, at the peak of its travel, you add a tiny bit of energy each time, and the swing goes higher and higher. But if you push at random, out of sync with its rhythm, your efforts mostly cancel out. A galaxy operates on this same principle of perfect timing. The central bar, or a passing density wave, creates a persistent gravitational tug, a rhythmic perturbation that sweeps through the disk. At most locations, a star or a cloud of gas feels this tug in a disorganized way, a force that comes and goes without a lasting effect. But at specific distances from the galactic center, something special happens. Here, an object's orbital period is a simple fraction of the period of the perturbing force. This is a resonance, a gravitational sweet spot. At these locations, the gentle tugs from the central bar or wave arrive with perfect cumulative timing. Instead of canceling out, each small push adds to the last, building up over millions of years to create a stable, reinforced pathway. The outer Lindblad resonance, for instance, often acts as a cosmic boundary fence. It is the point where the pattern's influence effectively stops, preventing the spiral arms from spreading out too far or dissipating their energy. This resonance confines the pattern, giving it a defined domain within which to operate. It is this network of resonant orbits that provides the underlying skeleton, the stable gravitational framework that prevents the beautiful spiral from being smeared away by differential rotation. The density wave is the music, but these resonances are the precise, unwavering tempo that keeps the entire symphony from descending into chaos. The cosmos refuses to be confined to a single template. Look across the universe and you will find a stunning spectrum of spiral galaxies, each with its own unique character. Some, known as grand design spirals, present themselves with breathtaking symmetry, their two majestic arms sweeping out from the center in a perfect, awe-inspiring arc. They are the cosmic equivalents of a meticulously planned metropolis, with broad, luminous boulevards of stars and gas. Then there are the flocculent spirals. These galaxies look as if they have been dusted with cosmic cotton, a patchwork of countless disjointed arm segments and star-forming knots without a single overarching design. They resemble a sprawling, organically grown village rather than a planned city. This dramatic diversity is not a flaw, it is a vital clue. It tells us that the hidden mechanisms we have been exploring do not all operate with the same strength in every galaxy. The final form a spiral takes depends on which forces are in the driver's seat. In a grand design spiral, a powerful, global organizer is at work. This is often the relentless gravitational engine of a central bar, funneling gas and sharpening the spiral pattern into a crisp, two-armed structure. Alternatively, a recent, gentle gravitational encounter with a neighboring galaxy can provide the external nudge needed to set up a clean, coherent density wave that resonates across the entire disk. The galaxy is being played like a single, harmonious instrument. In a flocculent spiral, that grand conductor is absent. Instead of a single, dominant density wave, the galaxy is a chorus of local voices. Here, the primary mechanism is a cascade of local gravitational instabilities. A cloud of gas collapses under its own weight, igniting a cluster of brilliant new stars. The shock waves from those stars' violent lives and deaths then trigger collapse in the neighboring cloud, which in turn lights up another stellar nursery. This creates a self-propagating chain reaction of star formation that paints the disk with hundreds of tiny, shimmering arm segments. It is a bottom-up process where local chaos creates a kind of fragmented, fuzzy order without any need for a galaxy-wide plan. This beautiful spectrum from grand design to flocculent shows us that there is no single recipe for a spiral galaxy. Cosmic artistry emerges from a suite of available tools. Sometimes a strong central government imposes order. Other times, a galaxy thrives through the decentralized enterprise of its local communities. The universe, it seems, appreciates variety in its masterpieces. Even these grand cosmic designs have a finite lifespan. A spiral arm is not a permanent monument, but a living, breathing feature of the galactic disk, born from chaos, shining with vibrant energy, and eventually fading back into the quiet background. Its entire existence is a story of dynamic change. The birth of an arm can be a dramatic event. It might be triggered by the gravitational instability of the disk itself, as a slight overdensity of stars and gas begins to amplify its own pull. Or it could be the sudden, violent gift of a galactic encounter, where a passing neighbor's gravity plucks at the galaxy, seeding the initial ripple that grows into a full-fledged spiral. Often, the most powerful and persistent arms are those launched directly by the relentless rotation of a central bar. which continuously pumps energy and gas into the pattern, acting as a steadfast engine for its growth. Once born, the arm enters a phase of brilliant maturity. This is when the density wave's compression works its magic on the interstellar gas, triggering firestorms of star formation. The arm becomes a luminous highway of young, blue stars and glowing nebulae, its structure defined and reinforced by its own prolific creativity. It is during this mature phase that the arm is most visible and majestic, a clear and coherent structure etched across the darkness. But this brilliance cannot last forever. Over hundreds of millions of years, the arm begins to age. The very mechanism that drives it may falter, perhaps as the central bar slows or the gravitational perturbation from a passing galaxy weakens with distance. More critically, the arm can literally run out of fuel. The cycle of star formation consumes the available gas, and the resulting supernova can blow any remaining material away, starving the pattern of the raw material that makes it visible. All the while, the silent, persistent force of differential rotation is constantly at work, applying a shearing force that slowly stretches and smears the pattern. The fate of a spiral arm is not always a quiet fade to black. A galaxy can experience a rejuvenation, a second act for its spiral structure, a new galactic interaction, a fresh influx of gas from a captured dwarf galaxy, or a significant internal rearrangement of mass can give the density wave a powerful new kick. This can resharpen fading arms or even spawn an entirely new set, resetting the galactic clock and beginning the cycle anew. This perspective transforms our understanding completely. We are not looking at static sculptures frozen in time. We are witnessing a fleeting moment in a continuous, billion-year dance of construction and dissolution. The beautiful spiral galaxy you see in a telescope image is not a finished product. It is a snapshot of an ongoing, dynamic process, a single frame in the epic, ever-changing story of cosmic evolution. The shape of this invisible foundation is far more complex than a simple sphere. The dark matter halo that cradles a galaxy can be subtly flattened, like a cosmic pillow, or elongated into a triaxial form, more like a rounded bar than a ball. This geometry is not a trivial detail. It is a fundamental property that directly steers the fate of the luminous galaxy within. The gravitational pull from a flattened or elongated halo does not just hold the galaxy together, it exerts a gentle but persistent torque on the stellar disk. Think of it as an invisible hand, constantly applying a slight pressure to the spinning plate of stars and gas. This subtle influence can either suppress chaotic instabilities or encourage the growth of orderly patterns like spiral arms. A slightly flattened halo, for instance, provides a more stable and predictable gravitational environment, one where a grand density wave can establish its rhythm and persist for billions of years without being disrupted. In contrast, a perfectly spherical or a highly irregular halo might introduce gravitational perturbations that prevent a clean, coherent spiral from ever fully forming, leading instead to a more flocculent, patchy appearance. This is a profound connection. It means that the specific, beautiful architecture of a spiral galaxy, whether it is a majestic two-armed pinwheel or a fragmented collection of starry tufts, is partly a reflection of the hidden shape of its dark matter foundation. The largest, most invisible structure in the galaxy leaves its direct signature on the most visible and celebrated features we can observe. This self-regulation is the galaxy's own built-in thermostat, preventing its stellar engines from burning too hot or too cold. When a massive star ignites within a spiral arm, it immediately begins to influence its own environment. Its fierce ultraviolet radiation and powerful stellar winds act like a cosmic blowtorch, carving vast cavities into the surrounding gas clouds and heating the material to immense temperatures. This process can actually stifle further star birth in its immediate vicinity by pushing potential star-forming material away. But the story does not end there. The life of such a star concludes in a supernova, a detonation of almost incomprehensible power. The shock wave from this blast slams into neighboring clouds of gas with unimaginable force, compressing them in an instant. This violent squeeze is often the final push that triggers the gravitational collapse of a new generation of stars. So, within the same stellar life cycle, you have two opposing effects. The star's radiation and winds initially suppress star formation, while its catastrophic death can trigger it anew. This creates a delicate, self-regulating balance. The galaxy is not simply converting all its gas into stars in one frantic burst. Instead, it is managing its resources, ensuring that star formation proceeds in a controlled, sustainable rhythm. This is why the spiral arms do not simply blaze with a single, blinding flash of light and then go dark. They shimmer with a sustained glow as new stellar nurseries are ignited just as older ones fade, all orchestrated by the feedback from the stars themselves. This cycle also enriches the cosmic ecosystem, seeding the interstellar medium with heavy elements forged in stellar cores and supernova blasts. The very atoms that make up planets and life itself are recycled through this process, a testament to how the galaxy's grand structure is intimately tied to the creation of its most intricate components. A galaxy's fate is not written in its stars alone, but in its cosmic address. The vast, empty stretches between galactic clusters are known as the field, and here, a spiral galaxy lives a life of quiet privilege. It spins in majestic isolation, its delicate arms free to coil and uncoil over billions of years, its reservoir of star-forming gas remaining largely untouched. This is the ideal laboratory for the internal mechanisms of dark matter scaffolding and density waves to operate without interruption. But place that same spiral galaxy inside a dense urban cluster, and its existence becomes a relentless struggle for survival. The space between galaxies here is filled with a searing hot, thin gas known as the intracluster medium. As a spiral plows through this plasma at millions of miles per hour, it experiences a phenomenal force called ram pressure stripping. Imagine holding a delicate dandelion seed head out of a car window at high speed. The wind violently rips the fluffy seeds away. In the same way, the pressure of the intracluster gas acts like a cosmic gale, relentlessly scouring away the galaxy's own cold gas and dust, the very lifeblood of future stars. This process can leave a spiral galaxy starved and gasping, its spiral arms fading as the fuel for new, brilliant blue stars is systematically stolen. The violence does not end there. In these crowded neighborhoods, high-speed gravitational encounters are constant. Galaxies do not collide and merge, they whip past each other at tremendous velocities, their gravitational fields reaching out like invisible hands, plucking stars from their orbits and distorting the delicate disk. This gravitational harassment further disrupts the stable orbits needed to maintain a coherent spiral pattern. Over time, the combined assault of ram pressure stripping and relentless tidal forces can completely transform a galaxy. The beautiful, ordered spiral is stretched, stripped, and shaken until its structure is erased, leaving behind a bland, featureless elliptical galaxy, a ghost of its former self. This dramatic contrast reveals a profound cosmic truth. The majestic spiral structure we admire is a fragile masterpiece. It can only flourish where the environment allows it, a reminder that on the grandest scales, beauty is often a matter of peaceful circumstances. Our own galactic home, the Milky Way, currently spins as a majestic barred spiral, a testament to billions of years of gravitational fine-tuning. Yet this beautiful configuration is merely a chapter, not the final page of our galaxy's story. Its destiny is written in the inexorable pull of gravity, a slow-motion dance with our largest neighbor, the Andromeda Galaxy. In roughly 4 billion years, these two colossal star cities will meet, not with a fiery crash of stars, but in a profound gravitational embrace. The delicate spiral arms we have come to understand, those intricate patterns sustained by density waves and dark matter scaffolding, will be the first features to be torn asunder. The gravitational tides of the merger will stretch and pull these structures into long, streaming tails of stars, a process called tidal stripping. This violent disruption, however, will also be an engine of creation. The immense compression of vast clouds of interstellar gas during the collision will ignite a firestorm of star birth, a final, spectacular starburst that will light up the merging pair with a ferocious, short-lived brilliance. After this crescendo, the system will settle into a new, stable form, most likely a giant elliptical galaxy, a smooth and nearly featureless sphere of ancient stars. This cosmic forecast places our galaxy's current splendor in a poignant context. The elegant spiral we inhabit is not a permanent monument. It is a temporary, magnificent state of balance, a fleeting equilibrium between the forces of construction and destruction that defines a specific, glorious phase in a galaxy's long and dynamic life. We have mapped the grand architecture, yet its fundamental origins remain shrouded in uncertainty. What is the true spark that ignites a spiral pattern? Does it always require the gravitational nudge of a passing galaxy, or can it simply bubble up from the inherent turbulence of the disk itself? Astronomers watch as some galaxies, left in perfect isolation, still manage to weave these majestic arms, suggesting a deep, internal rhythm we do not yet fully understand. Then there is the subtle force of magnetism, a ghostly presence woven through the void. Our maps of these galactic magnetic fields are still faint and incomplete. We know they guide the flow of gas and align the dust, but do they play a more active role in shaping the arms, perhaps providing a hidden skeleton that reinforces the entire structure? Their precise contribution is a whisper we are still learning to hear, and beneath it all lies the most profound unknown of all, the true identity of dark matter. We feel its gravitational embrace, we map its invisible halo, but we have no idea what it actually is. Is it a sea of exotic, undiscovered particles, or something even more strange? The very foundation of the galactic order rests upon a substance whose nature completely eludes us. These are not dead ends, they are the vibrant frontiers of discovery. They are the questions that fuel our most powerful new tools, from the James Webb Space Telescope peering into stellar nurseries to immense radio arrays listening for the faint signature of dark matter. Every simulation we run, every deeper image we capture, does not simply provide answers. It peels back a layer to reveal a new, more intricate puzzle beneath, reminding us that the story of the spiral galaxy is an epic still being composed, with its most profound chapters yet to be written. Our ability to witness this cosmic dance is undergoing a revolution, powered by a new generation of eyes and ears trained on the heavens. We are no longer limited to static portraits of galaxies. We are now assembling dynamic, three-dimensional movies of their lives. The James Webb Space Telescope acts as a powerful infrared lens, seeing straight through the obscuring dust that cloaks the earliest, most violent stages of star formation. It reveals the hidden cradles where stellar giants are born, showing us the very moment a collapsing cloud of gas ignites into a star, directly observing the feedback process that shapes the spiral arms. Meanwhile, on the ground, the upcoming square-kilometer array, a vast network of radio antennas, will listen to the faint whispers of cold atomic hydrogen. This will produce exquisitely detailed maps of the raw fuel as it flows through the density waves, allowing us to track the river of gas from the quiet outer disk into the star-forming fury of the spiral arms. And within our own galactic home, the Gaia mission is performing a monumental census, precisely charting the position, movement, and distance of over 1 billion stars. This incredible dataset is like giving us a gravitational map of the Milky Way, revealing the subtle tugs from dark matter halos and the resonant orbits that guide stars along their paths. These tools are transforming galactic astronomy from a science of beautiful pictures into a science of cause and effect. We are no longer just admiring the spiral pattern, we are watching it breathe, form stars, and evolve in real time, piecing together the live action story of cosmic order. This powerful tool allows us to perform the ultimate reality check on our cosmic theories. Scientists take the raw data from their supercomputer simulations, the ones that model dark matter, gas dynamics, and stellar feedback, and they run it through a digital filter. They process this virtual universe to mimic the exact limitations and strengths of our most powerful telescopes. They can create a synthetic image that looks precisely like a photograph from the Hubble Space Telescope, capturing the same glow of starlight and the same dark, obscuring dust lanes. Or they can generate a data set that perfectly matches the infrared view of the James Webb Space Telescope, piercing through the dust to reveal the hidden skeleton of older stars. They can even simulate the radio wave signatures that a vast array of antennas on Earth would detect from the cold hydrogen gas. This creates an artificial galaxy, a digital twin born entirely from our current understanding of physics. The true test comes when they place this synthetic image side by side with a real photograph of a spiral galaxy from the depths of space. Do the spiral arms have the same sharpness and graceful curvature? Is the distribution of bright blue star clusters and glowing red nebulae a perfect match? Does the simulated galaxy exhibit the same beautiful, fragmented structure of a flocculent spiral, or the bold, sweeping arms of a grand design? If the synthetic observation is indistinguishable from the real one, it is a monumental vote of confidence. It means the hidden mechanisms coded into the simulation, the dark matter scaffolding, the density waves, the supernova feedback are truly capturing the essence of cosmic order. But if the virtual galaxy looks wrong, if its arms are too fuzzy or its bulge too small, that discrepancy is pure gold. It points directly to a flaw in our assumptions, a missing piece of physics we have not yet accounted for. Perhaps our model of stellar feedback is too weak, or the influence of magnetic fields is more crucial than we thought. Maybe the dark matter halo has a shape we did not predict. This process of creating and comparing synthetic universes transforms abstract theory into a rigorous, testable science. We are no longer just building models, we are building worlds, and then asking the cosmos if we got it right. Every physical law that carves a spiral arm also shapes our world. The elegant mathematics describing a density wave's persistence are the same principles that govern the swirling vortex in your kitchen sink or the vast, organized rotation of a hurricane. This is not a mere coincidence. It is a testament to a unified cosmic order, a single set of rules that operates from the smallest scales to the largest structures in the universe. When we unravel the mystery of a galaxy's longevity, we are not just learning about distant star systems, we are reading the fundamental operating manual of reality itself, discovering the universal tendencies toward pattern, balance, and dynamic stability. Even more intimately, the story of the spiral galaxy is our own origin story. Every atom of oxygen you breathe, every particle of iron in your blood, every speck of calcium in your bones was forged in the heart of a massive star that lived and died long before our sun was born. These elements were then scattered across space by supernova explosions, the very same stellar feedback that sculpts the galactic arms. This enriched material eventually became part of the interstellar cloud that collapsed to form our solar system, nestled within a spiral arm of the Milky Way. We are quite literally children of the galaxy. The processes that structure these magnificent whirlpools are the same processes that assembled our planet and ultimately us. To understand the hidden mechanisms of a spiral galaxy is to understand the deepest forces that conspired to bring us into being. This transforms our gaze from a simple act of observation into a profound act of self-recognition, a way to comprehend our own place within the grand, evolving tapestry of the cosmos. This cosmic blueprint for order is written into the very fabric of reality. The existence of spiral galaxies presents a profound philosophical idea that immense and complex systems can spontaneously generate intricate and persistent order from what was once pure chaos. This self-organization is not directed by any conscious plan. It emerges naturally, driven by the simple, relentless rules of gravity and physics, resulting in structures of breathtaking beauty and stability that endure for billions of years. It suggests that order is not a rare anomaly in a universe of randomness, but a fundamental and natural outcome of the universe's own underlying laws. The spiral galaxy becomes far more than a collection of stars. It stands as a cosmic emblem, a testament to a deep-seated tendency within nature to evolve from simplicity toward stunning complexity and harmony. From the formless, searing soup of the Big Bang, governed by basic principles, can arise the majestic, coherent pattern of a spinning whirlpool of stars. This invites a powerful reflection on the nature of order in our own lives and in our world. We see similar principles at work all around us, from the intricate, branching patterns of a snowflake forming from random water vapor to the organized flow of a bustling city that arises from the independent decisions of millions of people. The galaxy tells us that order is not something imposed from the outside, but something that can blossom from within a system, a potential waiting to be unlocked. It hints that the universe may have an innate preference for beauty and structure, a silent, mathematical music that plays out on every scale, from the spin of an atom to the grand design of an island universe. This perfect galactic order is an achievement written in motion, a dynamic equilibrium held in place by the constant push and pull of cosmic forces. Gravity pulls inward, fighting the outward centrifugal force of a billion spinning stars. The energy from stellar explosions pushes back against the relentless crush of dark matter. It is a system in perfect, vibrant tension, a balance that has persisted for longer than our planet has existed. When you gaze at the faint, silvery band of the Milky Way arching overhead, you are not looking at a static picture. You are seeing a living, breathing entity, a cosmic engine whose hidden rhythms and silent architects have been at work for eons. We have merely begun to translate the first few lines of its grand, universal story, a story that continues to unfold with every silent turn of the stars.